Welcome to the lecture on sequence of functions. Starting with introduction, let Fn mapping from E to R be a function for each n belongs to natural number and capital E be subset of R, then Fn of x is a sequence of functions on capital E to R. Clearly, for each x belongs to capital E, such a sequence give rise to sequence of real numbers. For example, Fn of x equal to x raised to power n is a sequence of function defined on closed interval 0 to 1 to R for each n belongs to natural number. If we put n equal to 1, the first member of the sequence is x. If n equal to 2, then the second member as x square, and if we put n equal to 3, the third member of the sequence becomes x cube, and so on. It is important to note here that now the terms of the sequence are functions rather than real numbers. Sequence of functions arise naturally in real analysis and are especially useful in obtaining approximations to a given function and defining a new functions from known ones. Then the next question arises in our mind that when will a sequence of function converges, or what is the criteria for the convergence of these sequences? So there are two different notions of convergence for a sequence of functions. First is pointwise convergence and second is uniform convergence. Starting with the definition of pointwise convergence, let Fn of x be sequence of functions on E, which is a subset of real number, to R. Let E0 be subset of capital E, and let F mapping from E0 to R. We say that the sequence Fn of x converges to F on E0 if for each x belongs to E0, the sequence Fn of x converges to f of x in R. In this case, we call f the limit of sequence Fn on E0. When such a function f exists, we say that the sequence Fn converges pointwise on E0. For each x belongs to E0, the sequence Fn of x converges and there is a uniquely determined real number limit Fn of x. Mathematically, we write for x belongs to E0, f of x equal to limit n tends to infinity Fn of x, or it can be represented in different form like this and this on E0. It means that the sequence of function converges pointwise to function f on E0. Let's just understand the definition with the help of an example. In first example, Fn of x equal to x by n on the set of real number capital R. The first member of the sequence is f1 is equal to x. Second member of the sequence is x by 2 and third member of the sequence is x by 3 and so on. So clearly, as n tends to infinity, fn of x approaches to 0, that is limit n tends to infinity, x by n is equal to 0 for every x belongs to R. It can be easily seen from this graph also. So for every point belongs to the domain which is set of real number, the sequence of function converges pointwise. Let's do some another example. Example 2. Let gn of x equal to x raised to power n for x belongs to R and n belongs to natural number. Clearly, if x equal to 1, then the sequence gn of 1 equal to 1, which is a constant sequence and converges to 1. Also, limit n tends to infinity x raised to power n equal to 0 for the interval closed from 0 and open from 1, and is also true for minus 1 less than x less than 0. If x equal to minus 1, then gn of minus 1 equal to minus 1 raised to power n, which oscillates finitely. Similarly, if mod x greater than 1, then the sequence x raised to power n is not bounded, and so it is not convergent in R. So we have discussed all the points coming from the domain for which the sequence may converge or diverge or oscillates finitely. Hence we conclude that if g of x equal to 0 for minus 1 less than x less than 1 and 1 for x equal to 1, the sequence gn converges to g on the set open from minus 1 to 1 closed. Then next is lemma. This is another definition for pointwise convergence of the sequence of function. A sequence fn of function defined on E subset of R to R converges to a function f mapping from E0 to R on E0 if and only if for each epsilon greater than 0 and each x belongs to E0, there exists a natural number k which depend upon epsilon and x both, such that if n greater than equal to k, then mod fn of x minus f of x strictly less than epsilon. It is to be noted that this natural number depends upon epsilon and x both. The intuitive reason for this is that the convergence of the sequence is significantly faster at some points than it is at others. We can also use this lemma for proving sequence of function about its pointwise convergence. Then next comes uniform convergence. Starting with definition, a sequence fn of functions on E, which is a subset of R, to R converges uniformly on E0, which is a subset of E, to a function f mapping from E0 to R if for each epsilon greater than 0 there is a natural number k which depends upon epsilon only but not on x, such that if n greater than equal to k, then mod fn of x minus f of x is strictly less than epsilon for all x belongs to E0. In this case, we say that Fn is uniformly convergent on E0. It is written as Fn converges uniformly to F on E0, or in this way also for x equal to E0. the difference between pointwise and uniform convergence is that in the definition of uniform convergence, this natural number k depends upon epsilon only, and if we see the previous slide, then we observe that this natural number k depends upon epsilon and x both. So it is an immediate consequence of the definitions that if the sequence Fn is uniformly convergent on E0 to F, then this sequence also converges pointwise on E0 to F. But the converse is not always true. We can see in the above examples. First example, where fn of x is equal to sine nx upon n. By the use of definition of uniform convergence, one can easily prove that it is uniformly convergent to constant function 0 on R, as fn of x minus f of x whole mod is equal to sine nx upon n whole mod, which is always less than equal to 1 by n, in which we use the fact that sine function is bounded. So for epsilon greater than 0, there exists a natural number k which depends upon epsilon, such that if this n is greater than equal to k, then mod sine nx by n is strictly less than epsilon for all x belongs to R. Hence, the given sequence of function is uniformly convergent on set of real number R. Then in example number 2, fn of x is equal to x square minus 1 upon n. One can easily use the definition to show that this sequence of function is also uniformly convergent on any finite interval a to b, where a and b belongs to set of real numbers. As we have to calculate the pointwise limit of this function, then how to calculate it? F of x is equal to limit n tends to infinity fn of x. And what is fn of x? X square minus 1 upon n. So as n tends to infinity, f of x will be x square. So when you put this limit function in this definition, you get mod fn of x minus f of x whole mod is strictly less than equal to 1 by n. And in the similar way, we can show that this sequence of function is uniformly convergent on this finite interval. Definition can be used in next example also, example number 3, in which fn of x is equal to tangent inverse nx. For x greater than equal to 0, one can easily prove that this sequence is uniformly convergent in any interval a to b, where this a is strictly greater than 0 but is only pointwise in closed interval 0 to b. There are many more examples in which we can use the definition of uniform convergent. Now, next come the test for uniform convergence for the sequence of function. With the help of this test, we can easily prove that a sequence of function converges uniformly or not. So, the name of the test is Amend test. It states that let fn be sequence of function defined on E such that limit n tends to infinity fn of x equal to f of x for all x belongs to capital E. For this, let mn is equal to LUB of mod fn of x minus f of x such that x belongs to E if it exists, then this sequence fn converges uniformly to f if and only if mn tends to 0 as n approaches to infinity. The important part of the statement is how to calculate this Mn, which is LUB means supremum of the set in which x belongs to E. It means we have to find the maximum value of this function in the interval capital E. Let's just understand this test with some example. Consider fn of x equal to x square e raised to power minus nx on closed interval 0 to infinity. Note that fn of x is greater than 0 for x greater than 0, fn of 0 equal to 0, and fn of x approaches to 0 as x approaches to infinity. Hence, 0 must be the global minimum for f. We expect f to attain a positive maximum in open interval 0 to infinity. We can find the maximum value of fn using calculus or second derivative test. So for this we have the first derivative as this. One can easily calculate the critical point. Here the critical points are 0 and x equal to 2 by n. This analysis shows that x equal to 2 by n must be the point of maxima. It can be verified by computing second derivative, which is given below in this expression, and at 2 by n the double derivative of fn is negative, hence x equal to 2 by n is the point of maxima. Then we have to calculate the value of mn, which is equal to fn of 2 by n, which is equal to 2 by e whole square 1 by n square. So as n approaches to infinity, mn tends to 0. So with the help of mn test, we prove that the sequence fn of x converges to 0 uniformly on closed interval 0 to infinity open. Mn test can be used to check the uniform convergence of the following examples. In the first example, fn of x equal to nx upon 1 plus n square x square and f of x equal to 0 for x belongs to R. One can easily calculate the point of maxima by using second derivative test, that is x equal to 1 by n is the point of maxima for this sequence of function, and if we calculate mn for this sequence, then we get mn is equal to 1 by 2 as mn does not tends to 0 as n tends to infinity, then this sequence of function is not uniformly convergent on set of real numbers. You can check the uniform convergence of next two examples also. Then some important consequences of uniform convergence. These are some important results on the basis of which we can conclude whether the sequence of function converges or not. First theorem is, let fn be sequence of continuous functions on E subset of R, and suppose that Fn converges uniformly on capital E to a function f mapping from E to R, then f is continuous on capital E. This result can be used reversibly as if we calculate the pointwise limit f in the examples defined above, we see that if that function f is not continuous, then in that case sequence of function can never converges uniformly on the given domain. Then next important result is let Fn be a sequence of integrable function on closed interval a to b, and suppose that Fn converges uniformly to f on this domain, then f is integrable on closed interval a to b, and in this case integration a to b f of x dx is equal to limit integration a to b fn of x dx. So this result gives the interchange of limit and integral. Then come to the next important result, which is also known as Cauchy criteria for uniform convergence. So let Fn mapping from E to R be a sequence of functions from a set E to R, and then Fn is uniformly convergent if and only if sequence Fn is uniformly Cauchy on capital E. This result can be applicable from both the sides, that is, when sequence of function Fn is converges uniformly to f, then this sequence of functions Fn is Cauchy sequence, and from second side, if this sequence of function Fn is Cauchy, then the convergence of this Fn to f is uniform. Thank you.